All right, today we're going to go over our thermodynamics worksheet. First, we're going to start with temperature conversions. Don't forget you have the conversions here in your formula sheet. So for number one, we're taking 30 degrees Celsius and we're converting it into degrees Fahrenheit. And if we look at our equation, degrees Fahrenheit is equal to 9/5 degrees Celsius plus 32. So we just plug our numbers in. So degrees Fahrenheit is equal to 9/5 times the 30 degrees Celsius plus the 32. Put that in our calculator. We have 9 divided by 5 times the 30 plus the 32, and we get that that's 86 degrees Fahrenheit. Yeah, so that easy. The next one, we're taking 45 degrees Fahrenheit, and we want to take that into Kelvin. Okay, should not have the degree symbol there. Now when we do that, Fahrenheit and Kelvin don't directly convert, so we'd have to go from Fahrenheit to Celsius, and then from Celsius, okay, so Fahrenheit to Celsius, and then from Celsius into Kelvin. So we go find our Celsius into Fahrenheit equation. So degrees Celsius is equal to degrees Fahrenheit minus the 32, and that times the 5/9. So it's just the reverse of this one up here. And so when we do that one, it's just my 45 degrees Fahrenheit minus the 32, and then multiplying that times 5/9. And now let's put that in the calculator. So we have the 45 minus the 32 is that, and then we're going to multiply that times 5 and divide it by 9. And we get 7.22. Okay, as we do that, and then from there we want to add that to 273, right? So to get from Kelvin, it's just Celsius plus 273. So we take this answer that we got here, the 7.22, and then we add it to 273, and we get 280.22, or 280 probably good, or 280.2. Oops, and that's Kelvin, right? No degree symbol, and we're all good. Number three. On number three, we're taking negative 15 degrees Fahrenheit, and we're converting that into degrees Celsius. We just wrote down our equation up here, right? We're going to degrees Celsius, so that's equals degrees Fahrenheit minus the 32, and then that quantity times 5/9. So that is negative 15 minus the 32 times 5/9. So we have negative 15 minus the 32, negative 47 times 5 divided by 9, and we get negative 26.11. So your answer could be just negative 26 degrees Fahrenheit or negative 26.1 degrees Fahrenheit. And then number four, we have 61 degrees Celsius, and we want to take that one straight into Kelvin. And so that one's easy to go from Kelvin, to Kelvin from Celsius. We just add 273 to the Celsius. So that's just 61 plus 273, which should be what, 4 and 13 and 341? No, that doesn't sound right. Let me try. 4. Trying to get a 1. 1 plus 3 is 4. Let me do this in the calculator. I'm trying to do it in my brain. 334. I don't even know what I said, but 334. Okay, 334 Kelvin. And that's all there is to it. Now number 5, this is the one I kind of tried to set up for you as we go through. If we write down all our givens here, let's get 5, so I get it all on the page here. I'm going to flip this over so we can see the problem at the same time. So we have a 4 kilogram piece of tin. So we're going to have tin and we're going to have water. So we're going to have two sets of givens. Okay? So we're going to have the mass of the tin, and I'm just going to call it T, is equal to 4 kilograms. Okay? And then at 80 degrees Celsius. So the initial temperature of the tin is equal to 80 degrees Celsius. It's placed in 2 liters of water, which is 2 kilograms. So this is the mass of the water, is 2 kilograms. And its initial temperature initial of the water, is equal to 25 degrees Celsius. determine the final temperature. So my unknown is the final temperature of the system. Okay, so this is of the system when we add the two things together. Note 10 has a specific heat, so that's the little c. So that's 210 joules per kilogram degrees Celsius. Joules per kilogram degrees Celsius. And then the specific heat of water is equal to 4,184 joules per kilogram degree Celsius. And we're looking for that final temperature. Now the big thing we have to realize here is we're taking basically a bucket of water. There's blue here, let's get the blue out. So we got our bucket of water. We're dropping this piece of tin. We'll make tin green. Okay, so here's my tin. Here's my water. As we drop this 80-degree piece of tin in this 25-degree water, we're going to have heat transfer, or energies transferring out of the tin into the water. The tin is losing energy, so the tin is losing Q. So the Q of the tin, it's losing it. Okay? The energy the water gains is the exact amount of energy the tin gave up, because that's the system. The tin's losing energy, the water is gaining energy. Those two things must be equal. From our formula sheet, if we look at thermodynamics, we know that Q, well actually it's over here in thermal energy on this side, oops, right there. Q equals mc delta T, because those are the things I have, right? I have M's and C's and T's. So we know we're going to head towards mass water, specific heat of water times the change in temperature of water is then going to be equal to the mass of the tin, specific heat of the tin, change in temperature of the tin. Remember that we lost it, so all that stuff's a negative. We're going to take that to solve for this final. Now how do we get final out of that? Because I don't see final anywhere. But remember that this thing here, delta, means change in. So the change in temperature is equal to a final temperature minus an initial temperature. And then the final temperature, because we all equal out, because of the laws of thermodynamics, we want to balance and become thermal equilibrium, that the temperature final of the water will equal the temperature final of the tin. So that just is all equal to final temperature, which is what we're looking for. So it doesn't matter whether it's tin or water. Final temperature is just final temperature. Okay, so let's see if we can write all that down in one equation. Okay, so we had this. We're going to put this stuff into that, right? So we're going to put this into there. So that's where I'm going to start writing here. I'm not going to use all the colors anymore. Okay, so we have negative times the mass of the tin, specific heat of the tin, and now the change in temperature, it's going to be temperature final minus temperature initial of the tin. Or temperature final, it doesn't matter whether it's water or tin, so we don't have to keep track of that anymore. And then we have the mass of the water, specific heat of the water, and then we have the temperature final minus the temperature initial of the water. Now this is my unknown. That's what I'm solving for. And so now it's just a bunch of algebra to try to get that all by itself. So first we have to do that distributive property, right, to get kind of out of that parenthesis prison there. So we're going to have negative MTCTTF, and then minus and a minus, so this is going to be a plus, mass 10, specific heat of 10, temperature initial at 10. So I just multiplied the MC times everybody. You can do the same over here. Mass water, specific heat of water times temperature final, minus mass water, specific heat of water times temperature initial of water. And now I'm going to put all my temperature finals on one side and my temperature initials on the other side. And I'm actually going to go this way because I'm going to add that, because I'd rather have positive things. I don't like negative things. So I'm going to add this to both sides. Right? So we're going to add this, temperature final. And then we're going to get this guy to the other side. So we're going to add this one as well, right? Mass water, temperature, initial water, which makes it go away, right? So it goes away over here, just like this one goes away. Now we're going to add that same thing over here. Let's see, mass water, specific heat of water, temperature, initial of water. And now let's do all that. So over here we have that one away. So we have the mass of the tin, specific at tin, temperature initial of the tin plus the mass of the water, specific heat of the water, temperature initial of the water, equals, okay, the mass of the water, specific heat of the water, temperature final, plus the mass of the water, specific heat, the water of the tin, specific heat of the tin, temperature final. Sorry, we're getting kind of blended in there. Look, now I can pull the temperature final out of this guy because that's what I'm looking for. So I'm going to take this side, I'm going to take the temperature final out, and it's going to have mass water, specific heat of water, plus mass tin, specific heat of tin. I have the same stuff over here. Okay, so I'm going to write it really quick. And now I'm going to divide by this. How many letters can we have in here? That's going to make it go away over here, right? It's going to disappear over here. But that means I have to divide this side by it too. Oops. Okay, so I've just taken that and I've divided it. Now I have temperature final by himself, right? This stuff disappeared. So I have temperature final all by himself. So now I got to put all my numbers, all my numbers in there. So this was 4. I'm going to leave off the units just because it's confusing enough, right? There's too many numbers and letters in there. So we're going to have the 4, and then the specific heat of tin was 210, right? And then that times the initial temperature of the tin, which was 80. We're going to add that to the mass of the water, which was 2, times the specific heat of the water, which was the 4184, times the initial temperature of the water, which was 25. And then we're going to divide all of that by the mass of the water, 2, times the specific heat of the water, 4184. And then we're going to add that to the mass of the tin, 4, and that times 210 is specific heat, and that should give me temperature final. Okay, so a lot of craziness in there, so we just got to do our calculator. Be careful on this that you do order of operation correctly. So I try to break it apart. So I'm going to do 4 times 210 times 80. I'll get all this where you can see it. So that's this first part. So it's 67,200. And then I'm going to add that to, oops, I'm going to put parentheses around this. That's 2 times 4184 times 25. And I get this big, huge number over here, 276,400. I'm going to write that down just in case, we lose track in our calculator. 276,400. Okay, and we're not worrying about units so much right now. And then on the bottom, I'm going to get 2 times 4184. That I'm going to add it to the 4 times the 210. 4 times 210. And I'm going to get 9208. And that's what's going to be here on the bottom. Oops. Dyslexia stuff kicking in there. And then I'm just going to do this division. And then I should be all done. So I'm going to have the 276,400 divided by the 9208. And I get 30.02. 30.02, which we probably could just say 30 degrees in Celsius. And if we did all the units, but I know, they all work, it kind of confuses everybody to have all that stuff. So I'm not even going to look at them. Just we're looking at temperature. Temperature comes out as Celsius, and there we go. And that kind of makes sense, right? The final temperature, the water was 25, this was 80. It's got to be somewhere in between those two. As we went through, it is in between. The water has a huge specific heat compared to the tin, and so the water can absorb a lot more. So it doesn't go up in temperature because it can absorb a lot more energy or hold it compared to the tin. And there you go. That's number 5. I'm going to pause there and we'll do the other 6 through 12. We'll do those on another video.